I'm Shauna, and welcome to the first video of a series, An Approach to Troubleshooting Automated Industrial Processes. This is the very first overview of the series. In future additional modules, I'll actually be talking about each one of these steps in more detail. So I'll quickly go through everything here, and then we'll go more in depth in other ones. Now, this approach should work whether we're talking about something major, as is happening in this picture right here. It doesn't have to be that major, though. It can be just smaller system upsets, and this approach should work for all of that. The first thing we need to talk about is why follow this approach, and then we'll actually overview the approach and the observation of a problem, how to identify that, what response we should have, finding the root cause, and then correcting the problem, making the repairs, returning to service. And then last, we need to remember, once everything's going and everything's better, that we should do a failure analysis and continuous improvement so we can change things and not have any more problems. Why learn an approach? Why not just actually get out there, get things fixed, get back to business? What is useful about this? Now, if we follow a standardized systematic approach, it's going to be logical and step by step. This is very useful. When you're actually on an automated system, you may be in front of your board and the plant may be a feet away or a long way away. You could be miles away. You could be in a different state. You could be looking at your board. And so you actually have to know your system, know your equipment, and then be able to see upsets happening on the board and be able to conceptualize the problem that's happening without actually being at the equipment itself. The other really benefit is to articulate the steps to others. This is useful when we're filling out reports or permits. It's useful when we have, for say, a shift change. When you're having teammates come and go, we can tell our team that is coming on shift what we've done so far, where we're at in our approach that we're all using this together. So the first thing that happens in a troubleshooting situation or a system upset is there's an observation of that system upset. There's something that tells us there has something going wrong in our system. If we're watching the board, like this is an example here of a board that you may be watching in all the process flow diagram, your first indication may be an alarm, a high level alarm, a high pressure alarm, some type of alarm is going off, and you're seeing this on your screen. Another indication, if you're in the field with the equipment, is actually observing the equipment itself. If it's making different noises, it's the vibrations, if it's hot, if it's smoking, those may be indications of problems. The other one is a visual observation. If you look out the window now, in the first picture, if you see that fireball, that's a problem. That's a visual observation. You could see your flare going like crazy, and that would indicate a problem to you. So once we've seen that there is a problem, then we need to gather the information that we have. We have the information on the board, what we know in our head, and what we are familiar with the system, and then we can go and here's an example of the PNID. We can go pull out our PNID, which is going to have a lot more detail on it than our process flow diagram, and look at the data that we have on our board and what we know. And then we need to look at the first out. Frequently, then there's a system upset. Say the compressor went down. And of course, there's going to be a cascade of events that happen downstream, a cascade of alarms, because the compressor is no longer pressurizing the system, the gas is no longer flowing through the system, and we don't have any pressure or gas downstream, which is going to trigger a bunch more alarms. So we need to look at the first out. What is the first thing that happened, and our indicator of what that was. Once we've identified that there is a problem, we've observed it and identified it, now we need to do hazard identification and response. The first thing is we have to stop and ensure health and safety. And this is the very top priority. We go through these responses in order. These are the top 3 priorities we go through in order. Now, the very top priority anywhere is to ensure health and safety. You see in this picture here, the guys are really close trying to put out this huge fireball. Now, if there's an emergency, you should be able to cover it up with your thumb and it should be behind it. That's how far you need to be away to be safe. That's sort of just a general rule to keep you safe. And these guys are way too close. If there's a huge fireball and you're in danger, don't worry about your plant. Let the thing burn to the ground or the piece of equipment. Make sure your teammates, and the other people or public around, especially if you're in a city with a plant, are safe. Now, once you've secured your safety, the second priority is to minimize environmental impact. And I'm talking with when you're working with toxic substances, things that are regulated by the state or the EPA. You're required to make a response to minimize that impact. And this will be very specific to your industry and your plant itself. And you should have already covered these. There'll be policies and procedures within your company about what to do about this. Now, the third priority, again, these are in order, is to minimize equipment damage. And so if we're having a problem, we may need to shut down the system or whatever it is. If we're having a piece of equipment and letting that piece of equipment continue to run or not run or do whatever, we need to be able to focus on that. Because if we continue to let a pump run in a non-optimized situation, it's under pressure, under too much flow, while we try to do something else, and we actually break the pump, that is worse than completely shutting down that pump and fixing a minor problem that could make your system stop for a little while you fix it. But if you damage your equipment and you're waiting for parts to come in for days or months and your system's down, that is much more impactful than just taking care of your equipment in the first place. So once we've responded with taking care of first safety, second environmental, third equipment damage, now is the time to do a root cause analysis and figure out what actually happened. You have your process flow on your board, the data that's coming in from your system on your automated equipment, and then you have your PNID. It's time to figure out what systems are affected and what equipment is involved. Come up with a theory of probable cause. You may know, for example, that there's a piece of equipment, a pump's been going out, and the indicator is this pump itself. My theory is it's probably this pump. Now, there are methods and procedures to do the root cause analysis, and there are specific tools. So this is where I'll be able to teach you a lot more in depth about these tools. But for example, there is the serial method, the top to bottom or inflow outflow method, the bracketing method, the half splitting method. These are all tools to use. And for example, if you have top to bottom, this is a really good tool or method to use with a piece of equipment. You check the inflow and follow the process to the outflow and figure out where within a piece of equipment or a smaller system you have an issue. If you have a large gas plant that has tons and tons of equipment and you know halfway in between your compressor's down, you're not going to go to the very inlet of the system, start there and try to figure out which one it is. You may do a more half-splitting method. Is it upstream or downstream of half of this process? Okay, it's downstream. Okay, and then split it again. That sort of thing. So anyways, that's something that I'll be going into more in detail in the root cause analysis module of this training. Now, we're finally here. Time to fix and report. I know it feels like it probably took forever to get this, is because this, when you are working and you have a system upset, this is where you naturally want to be right away. I want to get in there. I want to get it fixed. I want to get it repaired. I want to get it back up and running. But now we've done all these previous steps that could go pretty quickly, but we just need to know that those are steps that happen in the process. Before we have a couple more steps before you actually get out there and get your hands on the panel or the equipment or whatever, you need to fill out your necessary paperwork. You're going to maybe do a job safety analysis. You may have some safety permits you need to fill out, some work orders if you need to order a new piece of equipment, if you need to work with a different team with maintenance to come in and fix something, or order contractors, that sort of thing. All of that will need to be completed. And then, of course, when you're ready to go out in the field, get your hands on the equipment, you need to be filling out your lockout tag. You're not going to go work on an electric panel without a lockout, tagout, or a large piece of equipment that is very dangerous. You need to have that in place. Then that's time to get out there and correct the problem, make the necessary repairs, and fix your equipment. So I'm glad you stuck with me this far, because I know that that's what you want to do. Just fix it and get on with life. Of course, we need to return to service. And you may actually have a cold start of your equipment. It may have been shut down. You need to do all of the procedures for a cold start. And you need to think about addressing temporary measures. If there was a bypass or valves opened, valves closed, anything that you've done in temporarily to the system you need to address those, to undo the bypass, make sure it's going back through the main line, do all that. Now, once it's in service and it's running, here's a really key point. Make sure you do your lockout, tagout, finish out your paperwork. Don't just go in there and, we'll race out for the day. You actually need to make sure that's finished and not leave your shift change hanging because you're gone and your paperwork's not done. There's other paperwork that you may need to finish up as well. So I know once everything's repaired and into service, it's like, that's so exciting. You just want to go on with life. But this is the time that you're not in crisis mode anymore to slow down, think about what happened, do some failure analysis, and continuous improvement. I know when there's a system upset, or especially the flow stops in your system, it's like in crisis mode. Just get the thing back up and running fast. And so you're moving and thinking and doing things quickly, but now is the time to actually slow down and do some continuous improvement. Along the way, hopefully you've been documenting, or you have notes, you have your paperwork that you filled out, and also you have documentation if you're working on an automated system that's collecting data such as SCADA. You have that's been documenting the process of continually. It is collecting data, and you will have that readout because you might not remember which things happened in which order. And we talked about the first out. That's a really important clue of which piece of equipment or which alarm went off first. And so then you're going to evaluate your system information that you have pulled together. There's various methods and tools for continuous improvement and failure analysis, and I'll be going into those and you'll learn more about them. Now, one real quick one is, it's super easy. It's a really great tool. It's called the 5 Whys. Yes, that's actually a technical term for a real tool. It's called the 5 Whys. Now, what happens is, for example, if you have a piece of equipment that is going out, let's see, a high-level alarm in a tank. You have a high-level alarm in a tank. Okay, that's the first. High-level alarm in the tank. Why? Because the outflow valve failed. Why? Because it's broken. Why? Because it was within the life expectancy. And that's the type of thing. But you may get to a why, and it wasn't. You learn it wasn't in the life expectancy. The thing was only 6 months old. Okay, what's the problem? Why is your valve or your equipment going out so quickly? And so you just keep asking why until you actually get to the root cause of what caused that failure. And then you can look at systems to improve that. Maybe you need some new administrative policies and procedures. Maybe you need a different pump manufacturer, maybe different things. You need some additional service, that pump needs to be serviced more often, that sort of thing. There are other methods, and we'll go into those continuous improvement methods. Thanks for sticking with me so far. I know for sure when something happens and there's a system upset, you just want to get at it. You want to go fix everything and move on. You don't necessarily want to have to follow a whole procedure or a approach through it. You just want to get on with your job, get everything up and running. Everybody's making money again. But here is a step-by-step approach, and the steps really quickly again as we observe a problem, we identify the problem, and then we have hazard identification and response. We find the root cause, and then that's when we get to fixing and repairing. Of course, we have to return to service, make sure everything's back up and running. And then the last piece is failure analysis and continuous improvement. It's really important that you actually go back and continuously improve, make things better, make life easier for you, better for your boss, better for your company, if you just spend that little extra time at the end. So now we will go in more detail of each one of these steps in the future modules.